Hi guys, in this lesson we're going to talk about tautologies. And a tautology is a statement which is always true. So for example, P or not P is a tautology. Because for any statement P, whether it's true or false, not P is going to be either false or true, and therefore P or not P is always true. So we get an always true statement. An English example of a statement with a structure would be something like it is raining or it isn't, which is what I've written right here. And either it is raining, which means it's true, or it isn't raining, which means it's true. So it's just a statement which is always true. Seems kind of funny or trivial almost, but these are actually really important to math. So let's look at another example. Here we take De Morgan's law, not P or Q, which we know is equal to not P and not Q. But instead of writing an equals in between, we write an if and only if. And whenever we do that, it becomes a tautology because the two statements are logically equal or logically equivalent. So we've been using equals to say that statements have the same value everywhere, but we could also have used if and only if and said that the statements are tautologically true. In other words, they're always true. And we're always looking for things which are tautologically true. So for example, we've said that if and only if is transitive, meaning that if and only if Q, let me make that clear. It's if P, if and only if Q, and Q, if and only if R. If all that, then P, if and only if R. That's an always true statement. It's kind of like saying if P equals Q and Q equals R, then P equals R. And this is going to be a tautology. It's an always true statement because it's a general rule in math. And so we could even write this with P equals Q and Q equals R. All of this implies that P equals R. I'm a little off the edge there, but so this statement is tautologically true, meaning it's true no matter what values for P, Q, and R that you plug into the statement. On the other side of things, we have contradictions, which are statements which are always false. So, for example, P and not P, which in English could be something like I'm 6 feet tall and I'm not. That's a contradiction, either you are or you aren't. P and P implies not P. So I left it there for you to check with the truth table, but you should get all falses if you do the truth table correctly. And if you negate a tautology, of course, you're going to get a contradiction. So if you take something which is always true and say not that, you'll get something which is always false, and vice versa. So if you negate a contradiction, you get a tautology. So remember that P or will distribute over an and. So we're distributing it inside these two places. So we know that P or Q and R equals P or Q and P or R. And so if I put the if and only if in here, then this is a tautology because those statements are logically equivalent. And if I take the whole thing, this entire statement, and then negate it out front, which is what's going on here, I get a contradiction because I'm saying not this tautology, which is always true, and since we're saying not that, it's always false. So we're going to use a fancy F to represent a contradiction, and we're also going to use a fancy T that looks like this to represent a tautology. Oh, there's one below. So this one's going to represent a tautology. So now let's look at a few computations with tautologies and contradictions. So let's look at a P exclusive or a tautology. That's actually equal to not P. So if we were to do a truth table, we would write down all possible inputs. And notice that even though we have two statements, we still only have 2 rows of possible inputs because the tautology can only be true. We can't plug in false for the tautology. So P is either true or false, and the tautology is true and true. Then not P is false or true, and P exclusive or true, well, true exclusive or true is false, and false exclusive or true is true, which is the same thing as not P. So these two things are equal. And another way to state that, if we wanted to use what we just learned, would be to say that P, exclusive or a tautology, if and only if not P, this is a tautology. So, okay, that's what I've written down here. P exclusive or a tautology, if and only if not P is a tautology. Another claim that we could show is that a contradiction implying a statement is a tautology. So remember that a contradiction is always false, therefore we have all falses in this row, and false implies anything is true. So whether P is true or false, false implies P is true, which is the same thing as a tautology, it's always true. Therefore a tautology, well, a contradiction implying P is a tautology. So there's some more practice you can do below in the problems with computing statements with contradictions and tautologies.